Hi everyone, I'm Sanya. This is cute little Yankee.
So cute.
And today we have a very special visitor and guest, one of my good friends, Dr. Shreya Mukherjee, who is a chemical engineer and a PhD. So Yankee's giving you a big round of applause. Dr. Shreya Mukherjee, thank you for taking the time today to talk to us and tell us about some of the work that you do.
Yeah, thank you, Sania, for doing this. It's a pleasure to talk about research always. But yeah, I try to keep it simple
Yeah.
and let's see how it goes.
I really appreciate it. And I know a lot of people out there are interested in this field, in the STEM field as well. So in this video, what Dr. Mukherjee is going to be talking to us about is why and where chemical engineers are needed. So why is this an important field? Some of the major areas of research for chemical engineers that are out there. And in fact, Dr. Mukherjee is going to open up about her journey as a chemical engineer, going through coming and doing a PhD in chemical engineering and going beyond. And it's a pretty exciting field, and I can't wait to learn about this from you. So thank you so much.
Yeah, thank you, Sania.
Dr. Mukherjee, can you tell us a little bit about yourself?
Yeah, sure. Thank you, Sania, for doing this. I have actually just finished my PhD back in August 2021, and my work was mostly focused on developing materials that were used for catalyzing electrochemical ammonia synthesis. But before I talk about all my research, just wanted to introduce a little bit of, about chemical engineering in general and what kind of research is done in the field. So I guess, yeah, we'll talk about all those in the slides. Right?
Well, this little guy is knocked out. Yes, so in this video, what we're going to have is, Dr. Mukherjee is going to go through and talk about and answer these three questions, give us some more insights about chemical engineering. And if you have any questions, comments, or all positive things as well, or just some questions to ask, please do put in the chat below. And Dr. Mukherjee will try to address them. And if you want some follow-up questions, we could consider doing another question and answer on chemical engineering with Dr. Mukherjee as well. So, please do reach out with any questions that you have or that you'd like maybe for us to have in another video.
Yeah, it was a nice experience. And yeah, feel free to reach out if you have any questions. So yeah, let's see how it's taken. Hello everyone. In this video, we will talk about my PhD journey as a chemical engineer. But before that, I would like to introduce you to what chemical engineers do and why and where they are needed, and also some of the major areas of research for chemical engineers. But before we do that, let's see a remarkable story which has really inspired me. So we all know about Alexander Fleming and his discovery of penicillin, but we often don't know the major challenges in bringing penicillin in industrial scale. So it took almost a decade of discovery to make it stable in the lab first after the discovery of penicillin, and then there were several challenges to produce it in the large scale. And if it does not produce in the large scale, it cannot reach people. And this is where Margaret Hutchinson uh, came into the picture. Like, she designed the first commercial penicillin production plant while working at Pfizer in the early years of World War II. So her major contribution was in the design of a large deep tank fermentation process, and which enabled large scale production of this drug. And just wanted to introduce Margaret Hutchinson. Of course, many of you definitely know about her. But if you want to take a deeper understanding of what the major challenges were, you can always look into it. So what we when we hear about chemical engineers, we often associate chemical engineers as chemists, and we think that they might be like dealing with chemistry, reactions, and beakers and Bunsen burners, like we used to do in school in our chemical lab. So let's see what is the difference between a chemist and a chemical engineer. So a chemist can produce a chemical in the lab, but to produce it in an industry, it requires a whole new ball game. So that's where chemical engineers operate. So how to produce or manufacture a chemical in the industrial scale, designing of the industry, separating the uh, raw materials, separating the chemicals from the raw materials, then uh, separating the intermediates, producing the product, separating the product, purifying the product, and how to make the process more energy efficient, how to treat the waste generated in the process. So basically everything from production to transformation to transport of chemicals, materials, and energy in the large scale, so that it can reach us all safely and at affordable cost. Of course, there are other engineers involved in the process too. So a plant cannot be of just chemical engineers. There has to be electrical engineers, there has to be control engineers, there has to be process engineers. But like process engineers, material engineers, control engineers can also be chemical engineers, mechanical engineers. So the major difference is scaling up a process in the industrial scale and dealing with the challenges involved in the process. So there could be trees which hire chemical engineers. It could be oil and gas industry. It could be pollution control. It could be cosmetics, paints and coating, pharmaceuticals, plastics and packaging. But all these industries, like, they help us in bringing those products, but at the same time, they also contribute to, pollution. And then there will be a whole group of researchers who would be working on pollution control, who would be trying to develop new materials to catalyze the process more efficiently, to reduce emissions in the car, to bring in more renewable energy, how to make energy more sustainable, how to go for carbon capture, how to utilize waste. So these are different areas of research in chemical engineering. And there could be many others. So today I'll talk about my area of focus during my PhD. So uh, before I introduce that, let's see why it was essential in the first place. So what we know about renewable electricity is that it is kind of intermittent. And in the first place, we are trying to make energy sustainable, we are trying to reduce emissions, and we are trying to go for electric cars, zero emission vehicles, and different other uh, processes to imbibe or accept more of renewable power. So here we just have included this graph to compare. Let's say you switch from conventional vehicles to electric vehicles. How much CO2 do you generate provided the fuel that you're using? Now, this accounts for not only the fuel used in the car, but the fuel, the CO2 emitted for the fuel production. So let's say this is a conventional vehicle and it will use gasoline. So how much is the CO2 produced when you're using the vehicle, as well as how much is the CO2 produced when uh, for generating gasoline? So similarly, if you are using an electric car, but the electricity is coming from, say, 100% coal or fossil fuels or the traditional energy that is known, then this is the total CO2 emission, which you can see is actually higher than the emission for conventional vehicles. So the point is, even if you switch to electric car, unless you use renewable or 100% renewable electricity to power those cars, there is no benefit in reducing the CO2 emission. And so where is the major problem? The problem is that renewable energy is not enough. So currently, the renewable electricity supply can meet only 20% of the electricity demand. And the major reason is transportation of renewable electricity, storage of renewable electricity. So those are the kind of challenges that researchers are working on right now. Now, there can be two methods of storage and transportation of renewable electricity. That is what is shown in the slide. So one is the short-term storage, where you say, let's say you use like solar energy and wind power to generate the electricity. You store it in short term, let's say in batteries. They use a converter, move it to the grid, and then from the grid you use the electricity. The other process is, can you change or can you convert this renewable electricity into chemicals, or say gas or liquid, which can be stored for a much longer time. It can be transported to gas stations, and then you can use like a conversion power plant either, and then from the power plant you can either send it to the grid, or you can use where needed, let's say fuel to the car, uh, or in the house, so at different places. So here we are mostly talking about vehicles or which are hybrid. Now, there are like different methods of energy storage. So like I said, there could be energy storage for low power or high power, for short term or long term. So if you go for short term and high power, you will go for supercapacitors. If you go for intermediate time period and intermediate power, you go for batteries. And if you want it to store for a longer period of time and you want longer power, then you'll have to go for chemicals like hydrogen. Now, what we know is that hydrogen is typically produced in the industries using natural gas, which again leads to a lot of CO2 emission. So an alternative method is to use the renewable electricity and obtain the hydrogen from renewable power. So in that case, you are generating less CO2. So this is what is shown here. So what we get typically from natural gas, the hydrogen that we get from natural gas is called gray hydrogen, whereas the hydrogen that we get, let's say, again from natural gas, but then you are doing carbon capture in the process, you call it blue hydrogen, whereas if you use renewable electricity to generate the hydrogen, then you call it green hydrogen. Now, it has its own potential for long-term storage and it has its own challenges. So my research was focused on addressing some of the challenges which I'll talk about. So let's say what is a major challenge for hydrogen. Now, hydrogen we know is like one of the least dense gas. So it comes on top of the periodic table, if you know. So what you can see in this graph is comparison of hydrogen with the typical fuels that is used in our cars. So volumetric density is how much of energy can you store per unit volume, and gravimetric density is how much of energy can you store per unit mass. So if you see for hydrogen, you have a very high gravimetric density, but you have a very low volumetric density, which means that you need a very high pressure to liquefy hydrogen if you want to store it and transport it, which is why people are looking for, and when you use such high pressure, again you're making it more energy intensive. So the idea is, can we use some other chemicals from those renewable energy and then break down those chemicals and get back the hydrogen. So that way you can store and transport those chemicals instead of storing and transporting hydrogen. So bypassing the major problem of hydrogen transport. So this is where we were trying to work on. So our major focus here is to develop catalysts, but I'll go deeper into that much later. First, let's understand what is happening here. So let's say I am using renewable energy, like I said, to develop a chemical, to synthesize a chemical called ammonia, which is well established process when it is used industrially in a Haber-Bosch process. But electrochemical process of ammonia synthesis is new, and I'll talk about the challenges here. So the idea is use renewable energy to make ammonia and then transport ammonia into, let's say, a gas station or a plant where you can convert ammonia to hydrogen and nitrogen. Nitrogen can be released in the air and hydrogen can be used as a clean fuel in the car. Again, the emission in the car is CO2 free because you are not using gasoline. So the idea is to use a zero emission vehicle, and the energy that is coming into the zero emission vehicle is also free from fossil fuels. Now, what is the major, so I'll talk about two projects here. One is electrochemical synthesis of ammonia, where my focus was in the catalyst design. And the other project is hydrogen generation from ammonia, where again, my focus was in the catalyst design. So you know that a catalyst is a material which can either activate or make the process faster or reduce the time in the process, make the process slower. So here, our major necessity was to increase the selectivity, and I'll talk about the strategy and the contribution. So the major challenge here was the contribution was that the selectivity in the reaction was less than 1%, and we were able to make it to 20%, which was equivalent to the industrial process. And then the other for the other reaction, generally a very rare earth metal catalyst is used for the reaction, and my work was to find a suitable material which can substitute the ruthenium catalyst without compromising the efficiency, and ensure that this material is stable so that you can use the same material without continuously changing it. So I had the opportunity to do my research with Professor Gangpo at the State University of New York. And we got this grant from the Department of Energy, and we collaborated with two different companies for carrying out these two projects. And we were doing it with a US DOE agency, which is called the ARPA-E, Advanced Research Projects Association. So I'll try to keep it more generic so that like it doesn't become very complicated and detailed. So when we talk about ammonia synthesis, the current technology is using a Haber-Bosch process, which is called the Generation 1 technology, which is what? When you use natural gas and you use a high temperature, high pressure process. So you take the energy from a high temperature, high pressure process to break down nitrogen and use hydrogen to get a reaction where you synthesize ammonia. So the next step is generation 2, where you also use a high temperature, high pressure process, but it could be using lesser energy, making it more energy efficient. And this time you're using renewable energy to break down the water into hydrogen instead of using hydrogen from natural gas or fossil fuel dependent fuels. So basically you are changing from fossil fuel dependent fuels to electrical energy, and you are synthesizing ammonia, but still at a higher temperature and pressure. And the third generation technology which people are looking at is, can we produce ammonia at ambient conditions? So now you are not using the high temperature, high pressure process, but you are using still renewable energy to split water to get hydrogen and use nitrogen to produce ammonia. So slowly what we can find is that irrespective of whether ammonia is used in the fuel or not, ammonia is used as fertilizer. So it's a major chemical used in fertilizer production. As the population grows, the fertilizer utilization will also increase. So overall, there will be a demand in ammonia production, whether it is implemented in vehicles or not, but there will always be a demand in ammonia production because of population growth and fertilizer production. Now, we have to make this industry more sustainable. So this is why a lot of research is going on to make blue and green ammonia. Now, how does this electrochemical process work? So I will not introduce all those terminologies here, but the basic thing that is happening is you're using renewable, let's say solar energy, and storing in the solar panel, you're generating electricity, and these electrons are going and meeting with a chemical, breaking down the chemical and producing another chemical. So water, let's say this is water splitting. So water is being introduced at the anode. It undergoes a reaction which is called oxidation, wherein you supply the electrons. Wherein it gets the electrons and breaks down into protons and oxygen. So you store the oxygen in a chamber, and the protons is transported through a membrane, meets the electrons that comes into it. There is reduction of the protons and the hydrogen is generated. So basically you are utilizing renewable energy to get hydrogen. Now, what we are trying to do here is that we will have a similar process wherein there will be a cathode and there will be a material on the cathode, which we call the catalyst, which we are trying to design. And then nitrogen will come at the cathode, meet with the electrons, get reduced, and then the water will also get reduced into oxidized, and so it will be reduced into hydrogen, and then this hydrogen and nitrogen will react to form ammonia. So the major challenge here is that although the desired reaction is the production of ammonia from nitrogen, but water gets easily split into hydrogen before nitrogen can be reduced. So about 99% of the energy that you are supplying here forms hydrogen instead of forming ammonia. So what we need is a catalyst which can make this process more efficient. And there are different ways this nitrogen can be broken down, and there are different reaction mechanisms. I'll not go into the detail about all these mechanisms, but now different researchers try to work on different mechanisms, different materials, and try to find an optimum process to make an energy efficient reaction. So our work was first to utilize another mechanism wherein we are taking a material with nitrides on the surface. So these will be metal nitrides. And then, so the nitrogen from the surface of the metal will first react with a proton and form ammonia. Now this ammonia will be released into the electrolyte, creating a vacancy in which another nitrogen can be absorbed and protonated, and this process should go on and on and on. And this it also has its own challenge. So if the rate of decomposition is higher than the rate of regeneration, it will basically utilize all the catalyst and the reaction will stop after a point of time. So my focus was to, develop a material which could make this process more stable. And that is how, is what we tried to do. So then we thought of utilizing metal nitride linkage on a carbon support. And these are called metal organic framework, wherein the single unit, let's say, is formed with zinc nitride linkage, zinc nitrogen linkage. These can form the building blocks of a metal organic framework, which will have huge pores. And this micropores actually help in the absorption of the guest, which could be nitrogen in this case. And we can actually pyrolyze this metal organic framework to get metal deposited on a network of carbon structures. And then the defects can affect the nitrogen absorption to enhance nitrogen reduction. So the idea was to use metal doped sulfate and use controlled pyrolysis, try out different conditions under which we can create the defects, and then using those defects to see which will be better for nitrogen absorption and increasing the selectivity of nitrogen reduction over hydrogen evolution. So like there are different ways it can be done. You can take different types of nanocarbon, you can use different doping methods, that can be different nitrogen sources. Based on that, there would be different transition metal carbon catalysts, there would be different types of reaction, different heating treatment. So all kinds of uh, uh, things that you can try out. That was a part of my research, which I tried out. But again, including everything will make this presentation like a 1 hour or long presentation, which I wanted to restrict. So just giving the key points of the research. So the typical metal organic framework. Yep, I kind of skipped the slide. But our major understanding was that we optimized the electrolyte. We used acid versus alkaline electrolyte and compared the production rate. We optimized the pyrolysis condition and compared the production rate. We optimized the Faradic efficiency. We optimized the potential and found the optimum potential for which we can get the maximum Faradic efficiency. So now it's important to see how the selectivity can be further increased. So we tried to further increase the selectivity by using a different strategy, where I tried to find out like what could be the element which can reduce the selectivity of hydrogen evolution reaction. And I was reading a paper, and their objective was to increase the hydrogen evolution, and they found that using nickel single atom can actually reduce. So for them, this was something that they did not appreciate, and they were looking for something like cobalt. But seeing this, I felt like, okay, maybe this will be useful to us. So again, we cannot use exactly this, so try to find out how can we make something like this, which, and if it can help in increasing the selectivity of the process. So this was the second work that I published on nitrogen reduction reaction. This figure is again similar to what I had shown before. So now we have developed like single atom nickel on which nitrogen can be reduced. And at the same time, there would be like nickel N4 coordination, which will limit the hydrogen evolution reaction. The mechanism I would like to skip here just to reduce the complexity of the process. And what we found here is that compared to different other catalysts reported in literature, we found a catalyst which was precious metal free and which was giving a comparable production rate. And then in the second work, compared to the precious metal catalyst, the non-precious metal catalyst like nickel, which we developed, was comparable. So we could get like comparable production rate and efficiency, and we were able to move from precious metal to non-precious metal. And this was the first time that this kind of carbon structures were used for as a catalyst for nitrogen reduction reaction. So this was something that we worked for a while, and parallelly we were working on the other reaction, which is ammonia cracking. But it's important to see how does the techno-economic comparison of different processes are. So if you, let's say, take the current generation Haber-Bosch process, which I mentioned uses natural gas as a fuel for production of ammonia, uh, which utilizes hydrogen from steam methane reforming. If you see, the total cost would be around, for a typical plant with 2,000 metric tons per day production, with the including the cost of carbon emission, because ultimately this is what is going to happen. You have to pay for the carbon tax for the carbon that you are emitting in the industry. So this would be the cost. Whereas if you go for electrochemical Haber-Bosch process, if you have a small plant, then it would be more expensive. Whereas if you go for a larger plant of a typical capacity as a Haber-Bosch, then it could be comparable to the current Haber-Bosch process, provided your nitrogen reduction reaction becomes around 60% efficient, which we have not been able to meet yet. So researchers are still working to make the process more efficient, so that one day we can use this kind of reaction in the industry and handle the challenges of carbon emission. So and typically you need about 8 to 12 megawatt hour per ton of ammonia, and you generate 3.8 tons of CO2 per ton of ammonia. And the idea is to substitute into no carbon dioxide per ton of ammonia, even if you are using the same amount of energy. And next we will move forward to the next project. But before we do that, this is the company that I'm working with now, and they are signing new contracts to implement this in the industry now, to use renewable electricity to split water into hydrogen, use this hydrogen to produce ammonia, store or transport the ammonia, and then bring it to the gas station, break it down to hydrogen, and use this hydrogen either for different applications, let alone just for vehicles. So there could be different applications. This is just an alternative method for shifting from gray hydrogen to blue or green hydrogen. So my solution here was to develop a non-precious metal-based catalyst that can be commercialized, so that we can shift from precious metals, which are currently being used, and it would be very expensive to scale a catalyst based on precious metals. So there were many literatures which were working on these kind of reactions, but it each had its own challenges, like the stability issues and cost issues. And our idea was to shift to a non-precious metal catalyst, and we were able to get like complete conversion at a temperature of around 500 degrees C with the non-precious metal catalyst. So these are something which is still under review, so I'll not go into detail about this. So I was fortunate enough to work with my professor Gang Wu and some other professors like Dr. Lun and many other members from different companies that we collaborated with, and my seniors and lab members. But so it all started from a undergrad who hardly knew what it's all about and what is ahead in the future. So I worked in a cement manufacturing company before this, and where I learned a bit about combustion chemistry, cement mill operation, and I could see like there is so much of CO2 emission, and I used to feel like what could I do to reduce like the carbon footprint of these kind of industries. So there were different skills that we get while we do our PhD, not just the technical skills, but mostly like handling different kind of problems, solving challenges, learning new techniques, and time management, people management, and all these things which you will always use going forward, no matter what are you doing in the future. So I guess using the skills and attitudes to find a sustainable solutions to meaningful problems would be the idea. But yeah, there is so much to do and so less time, and we have like huge targets to meet. uh, so yeah, let's see how we can contribute. But I'm thankful for this opportunity, and let's hope we can do something together and help save our environment in the future. Yeah, this is just the last slide. It's something which I work with and hope it inspires some of you and help you in your journey. So yeah, thank you.
Yeah, it's helpful. It's really helpful. Yeah, I
Wish you
think
good luck.
good luck to you as well. And I look up to you a lot. You know, you've kind of braved through, gotten your degree, and you know, it's a lot of perseverance. So thank you, Dr. Mukherjee.
Yeah, thank you, Sanya. Looking forward to the questions. Sure.
Bye, Shreya. Thanks
Yeah,
so much.
take care. Bye.
Take care.